Okay, another situation is where you have a block on an incline. Okay, so right here is the incline. Let's go ahead and make it a nice blue incline with a nice blue angle theta. Whatever angle theta is going to be related in a very obvious way to the angle between F grav and delta S. So, what's the angle between F grav and delta S? Is a function of theta, okay? Once you know that, then you know what the projection of F grav on delta S is going to be. You just have this triangle, you get the component of F grav in the direction of delta S. And also, you can easily get the component of F grav perpendicular to delta S. Now, this component perpendicular to delta S is very useful if you happen to have friction. If you don't have friction, you don't need it. Makes no difference. But if you do have friction, then this is going to help you find the normal force between the block and the incline. Okay? And why is that? Well, because the normal force is perpendicular to the direction of the incline. Now delta S here, and I didn't state it, is implicitly the displacement from this point, say, to the end of the incline, or between 2 points on the incline, whatever 2 points you want to use. Okay, so there's your delta S, and it's parallel to the incline. This component of F grav is perpendicular to the incline. The normal force is the force exerted by the incline on the mass perpendicular to the incline. The mass stays on the incline. It doesn't go down through the incline. It doesn't come up off the incline. So the net force perpendicular to the incline has to be zero. The only two net forces you have in the frictionless case, if you're not, in the case where gravity and the normal force are really the only forces acting, is the normal force and this component of the gravitational force, which means that the normal force will be equal and opposite to this gravitational force. Now, if you happen to have friction, that's very handy because the frictional force is going to oppose motion, and it's going to be a multiple, its magnitude is going to be a multiple of the magnitude of the normal force. It'll be 20% or 0.6 or whatever of the normal force. Now, this suggests that if you want to analyze this using a coordinate system, an XY coordinate system, the sensible orientation of the system would be with X in the direction of delta S, so that Y is in the direction of your normal force and of your perpendicular component of the gravitational force. It works out much more easily if you use a coordinate system in this direction because it makes the calculation of the normal force very straightforward, and your displacement is in the direction of one of the axes, the x-axis in this case. So, just a little advice and a little bit of reflection on what you have. You don't need a coordinate system to understand what's going on. Okay, all you need is this picture, and you pretty much get everything. But it's very convenient to do this with a coordinate system. We haven't done that yet because I want you to understand that these vectors are the ones that govern everything. Okay? And we want to understand the relationship between these vectors without complicating things with a coordinate system. But having understood that, then the coordinate system becomes a very convenient way to approach problems of this nature, and that's what your book does. Okay? I want you to understand it independent of the coordinate system so you can then understand why the coordinate system wants to be oriented the way it is and how to use it.